We're very pleased to have such a large crowd for Math for Everyone. If you stick around at the end of the talk, if everything goes according to plan, there should be pizza in the hallway. So now let's get to the talk. We're very pleased to have Steve Trettel from the University of San Francisco, who studies geometry and topology, and he also likes computer graphics and long bike rides. Steve, please take it away.
All right. Thanks, everyone. Can you hear me well enough? Is my microphone picking up? Sweet, sweet. Okay. Well, thank you all so much for coming to an evening math talk. This is always a good way to self-select a serious crowd, is to host your talk at night. So I know y'all are serious, so I want to teach you some serious math. I want to tell you about something I'm really excited about. And what I'm excited about is what's happened in geometry recently. So like anything, it's good to talk about history first. If I want to talk about recent, we should talk about where we came from. Where did us geometers come from? From a long, long time ago. When you usually think about geometry, probably the first thing that comes to mind is a scene like this, like Greece, and people drawing lines and circles, maybe Pythagoras, maybe Euclid, or my boy Archimedes up there. And that style of math, the first real, rigorous mathematical subject, changed the world and was studied for almost 2,000 years in that form. The geometry of the plane, perfected by the Greeks and used in architecture and in art and in science, in the development of physics by Newton and beyond. And then something changed. And then, sorry, is it not picking up? Oh, geez. Let's see. Oh, that sounded better. I don't know. It sounds so low. Okay, yell at me if it's not working again, and then we'll. Okay, great. Okay, so then a big change in geometry came in the 1800s with Gauss studying surfaces like this surface near where I live. Bumpy surfaces, not regular surfaces like the flat plane. And this period of math, taking things other than the flat plane seriously, spawned a bunch of beautiful mathematics. We're actually at about the 200-year anniversary of Bolyai writing a letter to his dad saying, "Dad, I discovered a new universe." By that universe, he meant the hyperbolic plane, which you'll see a lot of in this talk. So the story, when people hear about geometry, they usually hear about the previous 23 centuries, not the most recent 2. And I want to tell you about the geometry from 1823 until 2023, the stuff that really makes me excited, the stuff that made me a mathematician. So this math really changed the world. One of the first changes we notice is Riemann came along, generalized this idea of new geometry, and that was used not that much later by Einstein in relativity. And these days, this observation has kind of infected modern mathematics. It's all over the place. It's hard. I mean, I'm biased. I'm a geometer, so I see geometry everywhere I go. But it's hard to look at math without seeing the effect of the last 2 centuries of geometry. I want to tell you about 2 applications that are near and dear to my heart today. I want to talk a little bit about geometry in topology, and then geometry in data science and machine learning. But before doing that, we have to talk about what changed. What was the new thing? Geometry was essentially the same for 23 centuries. And in the last 2, it went from circles on the plane to black holes. What changed was curvature, thinking about curvature. Thinking about spaces other than the plane as geometric spaces in and of themselves. So a question Gauss asked himself when being a surveyor for the German government is, how do I understand these surfaces like the rolling hills? How do I quantify the fact that these are different than the plane? That's our starting point, taking that seriously. Well, how do we do that? Let me see. Where's my phone's not clicking. Let's click here. Yeah. Well, in Euclidean geometry, what do we know? We know that the ratio of, what's the circumference of a circle in Euclidean geometry? It's 2 pi r, right? Like that's one of those things that like, I don't know, I memorized as a kid. I think I learned it before I knew what it meant. I could just like spit out C equals 2 pi r from grade school. What it means is as you make a circle larger, its circumference grows linearly with its radius. So we're going to think about it as this plot here. C equals 2 pi r tells me how quickly space grows as I move away from a point. The circumference grows linearly as I move away from a point. Area, A equals pi r squared, means area grows quadratically. The amount of area I own if I like wall off a region of size r grows quadratically with r. But not if I lived on a hill. If I was building my castle at the top of some hill, and I measured radius along the hill, and then I measured circumference around the hill, and I asked, how does circumference grow with radius on my little medieval castle hill town? I would find that it grows slower. Imagine a sphere. If you stood at the North Pole and you walked down to the equator, and now you measured a circle. The equator is a circle. All those points are constant distance from the North Pole. But circumference over diameter? What's circumference over diameter there? Or circumference over radius? The radius on the surface of the Earth is a quarter of the way around the Earth, right? It starts at the North Pole, goes down to the equator. The equator is 1 time around the Earth. So C divided by R is 4, not 2 pi, smaller. In fact, if we did this on a sphere, circumference is 2 pi times the sine of R. This graph tells us how circumference grows slower quantitatively than Euclidean space. And if instead of living on a sphere, we looked on a saddle, on a little Pringle chip shaped like this, we could ask, how does circumference change with radius? And it grows faster. In fact, if your space had constant negative curvature, it grows with 2 pi hyperbolic sine. It grows exponentially. You can see in this picture, these circles get bigger because they have to go up and go down as they move around. So how can we use this information? We can use this information to assign a number to every sort of surface. We can say when circumference grows linearly with radius, then we're going to say the curvature is 0. When it grows slower, the curvature is positive. When it grows faster, curvature is negative. Now, as mathematicians, we just don't want this is like a vibes definition. Like I'm just saying, when the graph looks like this, we say it's like this. That's not good for math, right? We want a quantitative definition, not just a feeling. So how do we make this quantitative? We can take a limit. As we want to measure the curvature at a point on our surface, we look at circles, and as they get smaller, we measure circumference over radius. We see what happens. Also, shout out to my geometry students. They actually have an exam on this formula today, and I told them I was leaving, but I was going to talk about our class. So good luck, everybody. This is how we quantitatively measure curvature, measure difference from the Euclidean plane. We take 2 pi r, the Euclidean circumference of a circle, and we measure its difference from the circumference on our space, and then divide by a normalizing factor. And this idea of taking curvature seriously, taking other spaces seriously, allows geometers to claim many things in the world as objects of our own study. Instead of being stuck studying the plane or tilings on your bathroom wall, geometers can now talk about spheres, shapes with positive curvature, corals, kale leaf, saddles, shapes with negative curvature. But instead of these real-world examples, mathematicians, to get a first handle on things, we often like to idealize our situation. So we'll look at an ideal, a perfect sphere, a perfect plane, and a perfect piece of negative curvature. Oops, oh my gosh. My presentation moved ahead 2 slides. Sorry. Here we go. Here are the perfect versions drawn by Escher. Uniform positive curvature, uniform zero curvature, and uniform negative curvature are 3 types of geometric space. And we can build these in 3 dimensions as well. So How do we build a space of zero curvature in 3D? Well, this one's easy. We live there. We live in a space that looks like stacks of cubes everywhere. Euclidean three-dimensional space. Linear algebra's favorite space when you're first learning about this stuff. How do we build a space of three-dimensional space, a space that we could live in that has positive curvature? Well, if the sphere has positive curvature and is 2D, I'd like to build an analog of the sphere. And here's one way to do it. The sphere, what happens when I slice a sphere into slices? You can see a bunch of circles, right? There's a dot at the South Pole. It gets bigger as you move up till we get to the equator, biggest circle, biggest disk, and then they shrink to the North Pole. That's how we can understand the two-dimensional sphere. What if I replace those circles with spheres and stack them in the fourth dimension? Just like a stack of circles in 3D builds a sphere that we can see. A stack of spheres in 4D builds an analogous space, which I don't expect anybody to be able to picture. That's hard, right? Stack of spheres in 4D. I don't know what that looks like. We can write down the math. We will write down the math, and I'll show you a way to picture it later. And then a 3D negative curvature space, we could take a space in 2D that we know has negative curvature and spin it around, build a space in 3D. So there's examples of positive, negative, zero curvature, not just in the plane, but in higher dimensions as well. But my goal is to try and seriously engage with these spaces. I want us to leave this talk understanding what it would feel like or what it would look like to be inside of one of these spaces. And to answer that question, we need to talk about what is vision. How do we see objects? Like when I'm looking at my water bottle, I see it in a certain direction in the room. This is going to sound really pedantic, but I swear this is important for later. When I look at the floor, I see the floor down. Why do I see the floor down? You might say it's because the floor is down. That's also what I thought. But being pedantic is good for mathematics. Being precise is good for mathematics. The reason I see the floor down isn't because the floor is down. That's also true. But it's because the straight line connecting my eye to the floor leaves my eye in the downwards direction. That's why I see the floor down. If the straight line connecting my eye to the floor left my eye in the upwards direction, that'd be weird, but I'd see the floor up. So what is vision? Vision is a geometric sense. Vision is a way of probing the world with geodesics. In the real world, light comes into our eyes, but it's easiest for us to picture kind of the time reverse of that. Like imagine your eyes were like shining light out and seeing things. So where do I see the ball? I see the ball where the lines, the straight lines connecting the ball to me, hit the ball. Okay, I swear it's going to get more interesting, I promise. But first, let's do some high school trigonometry from that observation. Once I know that the way vision works is by thinking seriously about Euclidean geometry of straight lines, I can ask myself, how big does a ball look? If a ball is distance d away from me and is radius r, how big does it look in my vision? And I can find a formula for that. I can do the trigonometry. And I can find theta, the angle it takes up in my eye, is approximately 2r over d. What does that mean? That means we can prove, mathematically, an observation that we all have known since childhood. If something's twice as far away from you, it looks half as big. Like, I know the people in the back row aren't actually a quarter inch tall, even though I can cover you with my thumb. Like, I know you're the same size as the people in the front row. It's just you're farther away. And my brain is doing this formula for me because my brain knows Euclidean trigonometry because that's where I live. The other thing we can prove from this is you can see less than half the sphere from any point. If you have a ball in front of you, look where our lines of sight are hitting the ball. They're hitting it before the equator, right? Tangents coming from your eye form a cone. That cone hits the ball, and you see less than half of the ball. When it's really close to you, you see really less. Like if someone's like right up in your face, you don't see like much of their face. And someone's far away, you see almost half of a sphere. And so a good example here is Apollo coming back from the moon. We're far away from the Earth, and you can see slightly less, but almost half of the Earth. You can see the South Pole, but you can't simultaneously see the North Pole. But what about if we weren't looking at flat space, if we were looking at curved space? Well, in positive curvature, circles grow slower than Euclidean space. Space grows slower as you move away from a point. And what that means is lines of light, straight lines, move apart slower than they do in Euclidean space. In negative curvature, where circles grow faster than Euclidean space, straight lines move apart from each other faster. So what I've animated in the top here, I have the Earth, and imagine you're standing at that point where all those lines are coming from. Those lines are like lines of sight. Those are light rays connecting to you. And I'm like a mad scientist in my geometry machine, and I have a dial, and I'm changing the curvature of the universe as this animation plays out. When those lines of sight are closing back in, I've dialed the curvature of the universe up to positive. When I move my dial over to negative, lines of sight, GD6, move apart. I want you to imagine, what would you see if you were standing there and I was running my crazy universe machine? What would the Earth look like to you? Does anyone have a guess? As I change the curvature to become negative, so light rays spread apart, what happens to the Earth in your vision? Shrinks. Yeah, I'm seeing a lot of the right hand motions here. People being like, whoop, whoop. Absolutely. Less angle of your vision hits the Earth. So the Earth looks smaller in your field of view. When I turn my crazy dial up to positive and the light rays bend inwards, they move apart slower, the Earth looks bigger. So you'd be standing at that point and the Earth would look like it's oscillating in size. It's not. The Earth's the same size. You're not also getting closer or farther. But the angle, the amount of light that hits the Earth is changing. This tells us something about geometry causing almost an illusion. And this is our first hint of just how weird the world's going to be when we curve it. So let's think a little more seriously about this. It's easier to think in 2 dimensions where we can see a space of positive curvature, like straight up. So here is a positively curved sphere. And I want to imagine that you're standing at the North Pole and you are watching this green ball. As the green ball moves away from you, at first, it gets smaller in your vision. Less of these light rays are hitting the green ball. But once it gets past the equator, what happens? When it gets past the equator, lines of light start moving back together. More of them hit the ball again, and the ball looks bigger. So this is what we'd expect. As you move away, it gets smaller. At the equator, it looks smallest, and then it starts looking bigger again. Oh, we'll see. It wraps more than half the sphere at some point, not right past the equator. Actually, if we look at this, if the ball is distance x away from you, and if it's like x away from you, or if it's x away from the South Pole, it looks the same size. And we can work that out. We can work out spherical trigonometry. So anyone who likes trigonometry, here's a homework assignment for you. Work out the formula on a sphere for how big a disk looks at distance d away. Don't worry, I did your homework for you. I made you come to a talk at night, but I'm not actually going to make you do homework. Here's the answer. It's approximately 2r, not over d, but 2r over the sine of d. So we can calculate this quantitatively. And so one more thing to look at, one weird thing here. When I'm doing this calculation, how much of the sphere are we seeing? When we're really far away from the sphere and the light's bending back in, those 2 rays of light, those yellow lines, are hitting the sphere more than halfway around, right? They're hitting the sphere on the back side because they've curved around and bent in. What does that mean? Well, instead of looking at a green ball moving away from you, let's imagine what happens if you were looking at your friend. If you were to walk away from your friend in a positively curved space. At first, just like the green ball, your friend's face would shrink. But once you pass the equator, your friend's face would grow. Even though they're getting farther away from you, they'd look bigger. But worse, you see more of their face. Right? If light bends around and hits a sphere on the backside, light bends around and hits your friend's face on the backside. And the farther you go, the more of your friend's face you see. What happens when your friend makes it to the South Pole? If you're at the North Pole and your friend's at the South Pole, any line of sight you look on, what do you see? You see your friend's face. When your friend's at the South Pole, their face unwraps and engulfs you. It fills every point of the sphere. If you look up, you see your friend's hair. If you look back, you see the back of your friend's head. If you look to the side, you see your friend's ear. Because all lines of sight, all lines on the sphere that start at the North Pole hit the South Pole. Your friend becomes the whole world. So that's pretty terrifying. But it'd be way more terrifying if I was bored and I decided to animate it. So in this computer program, what I've done is I've taught the computer program the laws of geometry in a positively curved space. I've taught the computer program. Do you know what ray tracing is? Like when people are like making a video game or like making a movie, they simulate it by like shooting rays of light out into a computer scene to draw the picture. I wrote a ray tracer in positively curved space and I put a friend in there. And so what we're going to do is we're going to walk away from our friend at constant speed. No matter what you see, your friend is just getting farther away from you the whole time at a constant speed, I promise. At first, their face looks a little smaller. That's good. But then their ears start to wrap, which is kind of not the best. And then their face kind of appears inside out. That's a good homework problem. Think about why their face looks convex before their ears engulf your world. And now your friend's at the South Pole, and you cannot get away from your friend. Your friend's actually as far away as possible. This is the farthest they could ever get from you. And yet, they look the closest. I watch this video anytime I want to be thankful that I don't live in positively curved space. What would the Apollo mission see if they were coming back from the moon in positive curvature? They would see more than half of the Earth. Lines of light that manage to come apart and reconverge due to the positive curvature allow you to see the North Pole and the South Pole at the same time. So if I put you on a crazy spaceship and I dropped you off in space and you looked at a planet and you saw the North Pole and the South Pole at the same time, that's our hint that we live in positively curved space. If you see only one of the poles, like a normal world, that's like flat space. So this is the sort of intuition we want to develop from these sort of pictures. Light rays reconverging let you see more of a sphere than you expect. And so here's a collection of a bunch of balls in positively curved space. All these balls are the same size. And they're just moving away from you and towards you at a constant speed. But what you see is the balls in the background look the biggest because they're near the South Pole. They're like your friend's face. They're about to fill your world. So judging distance would be kind of difficult in a positively curved space. Instead of me being able to cover up the back row with my thumb, the back row would look like gigantic, huge people. The middle of the auditorium would look the smallest, the people near the equator. You would not be able to get away with sleeping in class in positively curved space by sitting in the back row. You'd have to sit in the middle. But what happens if I take my crazy curvature dial and I whip it over from positive space to negatively curved space? What happens in negative curvature is lines of light move apart faster. Things look smaller. All these balls you see not too far out, like they're almost like pixelated size in the background there, yeah? Like they shrink really small. All these balls are actually closer than some of the balls in that last scene. The farthest balls in this picture are like 5 meters away from you. They just look really small. And there's a lot of balls within 5 meters of you. That tells us something else. That tells us there's a lot of space within 5 meters of you. Why is that? Well, circles, remember, how did circles grow in negative curvature? They grow faster than Euclidean space. Space grows exponentially fast in negative curvature. So there's all this room for activities in negatively curved space. Thousands and thousands and thousands of balls. And what do you see? Not only do the balls look small, And we can quantify it, this time using hyperbolic trigonometry instead of Euclidean or spherical trigonometry. But how much of the ball do we see? We see less than half, right? If lines of sight are moving away from each other, when they hit the sphere tangently, you'll never see half of the sphere. You'll always see less than half of the sphere. You can actually work this out. Turns out you can see pi times the radius of curvature of space squared for people who like doing Riemannian geometry exercises. There's your homework, grad students. But here's the Apollo mission in negatively curved space. Instead of seeing both poles at once, Indonesia fills an entire hemisphere because you can see very little of the Earth as the light rays are racing apart. And as space grows exponentially as you move away from a point, you can build lots and lots and lots of things in negative curvature. Here's showing you how many cubes fit nearby to a central cube as you build out. Instead of in Euclidean space, where it grows with the cube of space in 3 dimensions, this grows exponentially. Here's what I look at on the inside. You see lots and lots of cubes. So this is your sense if you wake up in a space and things look really, really, really small in the distance and there's a lot of them. That tells you you're in negative curvature. These are kind of this is like getting our bearings for positive versus negative. We have some clues, right? If somebody's head wraps around you, you know it's positive. If something looks giant when it gets far away, you know it's positive. If there's like a crap ton of things, you know it's negative. If things are really tiny, you know it's negative. But these aren't the only options. I don't actually remember all my literature classes, but I remember Shakespeare said something like, there's more ways for space to curve, Horatio, than you dreamt of in your geometry. There's more than just 3 ways for space to curve. It doesn't just have to be all positive, 0, or all negative. What could we do? I could take a space of negative curvature, and I could stack them on top of each other. I could build a stack of 2-dimensional negatively curved spaces. This space is going to have some other weird properties. Well, it's going to have negative curvature in 2 directions because I stacked negatively curved spaces. But in the stacking direction, it's actually going to look flat. There's going to be directions here. There's going to be planes up and down that are tiled by squares and cross sections that are not. This space is called by the very uncreative name H2 cross R, H2 meaning hyperbolic space, negatively curved space, and R meaning the real line. That's the stacking direction. So if a space has negative curvature in some directions and 0 curvature in other directions, we should try and imagine what we're going to see. If we look in the negative curved directions, things should get small really fast, right? That's what happens in negative curvature. If I look in the flat directions, things should get small at a normal speed, at what I'm used to, because I'm from flat space. So it's fun to try and work that out, but it's better to just simulate it. In this direction, you look, the balls get really, really small, really, really fast, but they're also stretched out into ovals. And if you look in this direction, the balls don't shrink so fast. You can pick out inside of this weird space, you can tell what directions are positively or what directions are negatively curved and what directions are 0 curved by looking. You can just look at the size of the balls, and that gives you a sense. Instead of stacking negatively curved spaces, we can also stack positively curved spaces to get another example. When I stack positively curved spaces, what am I going to see? I'm going to see one direction where stuff looks normal. And then in the positively curved direction, I'm going to see things getting really big, maybe wrapping around the world. This is actually the space I would want to live in least out of all of these things. It's a lot of weird properties. But in this direction, we're looking in the direction where there's positive curvature. Balls are getting stretched out and wrapping around your face. And now as we rotate, we'll look in the direction of 0 curvature. We'll see the balls looking normal coming out of the top corner of the screen here. There we go. That's the direction with 0 curvature, where the balls look normal. So that's how good detecting curvature with your eyes works. You can look at a space once you've had a little training in this, and you can just tell by what it looks like what the curvature is, positive, negative, zero, depending on the direction. But you can do even weirder things than this. Instead of just stacking, you can stack things in strange ways. My personal favorite three-dimensional space is kind of like a twisted stack of planes. It's called nil geometry. And what I'm drawing here is the rays of light from your eye. Imagine you're that white ball in the middle. These curves are the straight lines in nil geometry. These are the lines that light would come to your eye. We see sometimes all the straight lines are collected together in one direction. They're all kind of converged, like right there. They're like a laser beam in one direction. And then sometimes they're spread out all over the place. What does that mean? That means in some directions, there's positive curvature. They're all kind of together. And in other directions, there's negative curvature. They're all splayed apart. This space is very confusing to get used to the first time you see it, so I want to do just one thought experiment exercise here. I want to try and imagine we're on the Apollo mission. We're coming back from the moon, and we're looking at the Earth. I want to imagine what we would see. So you're the white ball, again. These rays of light are going from you to the Earth and back. Watch what happens. In the middle, well, right in the middle of your field of view, that middle ray of light hits the Earth. So you see the Earth right in front of you. That makes sense. But there's some other rays of light that hit the Earth too, actually in your peripheral vision. Those orange rays of light, the ones that are farthest away from your field of view, those are curving around and they hit the Earth, right? So what do? I see the Earth in the middle of my vision, and I also see the Earth in the peripheral of my vision. But what about in between? What's happening with those yellow lines? It missed the Earth. Does anyone have a guess what it would look like if I were in this crazy world? What do I see for the Earth? Yeah, like a bullseye. Absolutely. I see the Earth right in front of me. And then I see a whole ring where light misses the Earth. And then in my peripheral vision, I see the Earth again. That's almost too weird to picture, so let's plug this into our ray tracer as well. Here, just like your friend, we're just going to move away from the Earth at constant speed, no matter what it looks like. And eventually, we're going to stop when we get the Earth to the position that we were just simulating. So at first, the Earth looks smaller, as we'd expect. We're moving away from something. Of course, it gets smaller. Now it looks like it's getting bigger, but we're still moving away. Uh-oh. Now it looks like a bullseye. Absolutely right. What happens is some rays of light that were leaving very, very far away reconverge due to positive curvature and re-hit the Earth. You see the Earth in the far part of your vision. You see the Earth in the middle of your vision. And the light rays right in between skipped on past the world. I would not want to fly a spaceship here. Here's what it would look like in the asteroid belt. Too many balls. So you can see what direction, you can see where we were seeing those rings, right? That direction has positive curvature. And then you can see in other directions, the balls look really, really, really small instead of being magnified. Those directions have negative curvature. And in general, there's lots of spaces like this. There's lots of spaces that have some directions positively curved and some directions negatively curved. So here's another one. The space has the uncreative name SL2R because, well, it's the group of matrices SL2R. This is the space of 2x2 matrices with determinant 1 as a geometric space. It has a metric on it that has positive curvature and negative curvature, and this is what it looks like. The space where it looks all spirally, wormholey, that's the direction of the rotation matrices in this space. This is what I mean. There's geometry everywhere, guys, even inside matrices. Here's another space called soul geometry. This also has positive curvature in some directions where balls are big and stretched out, negative curvature in others. So this is the big wide world that we didn't grow up in because we grew up in flat space. But this is the big world of mathematical possibilities out there. All these sorts of mixes. So this, in my opinion, this is the big advance that we made in geometry in the last 2 centuries, was going from thinking about the plane to treating all of these as equal citizens in the world of geometry. All of these are spaces that we need to understand. And that perspective has allowed us to do a bunch of really cool math, which is what I want to do with the rest of the talk, is tell you about 2 spots outside of geometry that this sort of thinking matters. Oh, first, sorry, I forgot. Shameless plug. If you want to hear about how to make these pictures, if you're like, wow, those pictures look cool, but like I'm a details guy and I want to know exactly what's going on, I got great news for you. We have like a 140-page paper that explains everything. So you can check it out. It's called Ray Marching Thurston Geometries. It's a collaboration with Remy Coulon, Sabeta Matsumoto, and Henry Siegerman and myself. But okay, back to the fun stuff. So application of geometry. My personal favorite stuff in math is when we think really hard about something for one purpose, and then it turns out that that stuff is important somewhere where you least expect it, somewhere totally different. Like we made all of this progress thinking about what could space be. And then, of course, that's useful for understanding what space could be. That's what I was after. But it really gets me going when that stuff shows up somewhere else. So the first application I want to show you is thinking about topology, thinking about shapes in general, but not thinking about their metrics, not thinking about space. So here's a question that you would study if you were a topologist. You'd be interested in surfaces, you'd be interested in curves, and something you'd like to do is know when is a curve stuck on a surface versus when it's not. A curve is stuck if you can't like shrink it to a point or pull it off the surface. Or equivalently, if you cut along the curve, some curves disconnect your surface and some don't. We want to try and understand all the curves that don't like just cut off a piece of your surface, that are kind of stuck on there. Back in the 1890s, Henri Poincare realized that this was a really good way to think about surfaces, to think about shapes. That if we could understand the curves on our space, we could understand our space very well. But of course, the problem is, how do we find all the curves on our space? Here's a loop that's stuck on the torus. Here's a loop that's stuck on a donut. So here's one loop, but like, what else is there? There's probably a crap ton of loops on the donut. And I want to understand all of them. My goal is to find them all and list them all, every single loop that's stuck on the donut. Any curve you could possibly draw on a donut shape that when you cut along it, the donut doesn't fall into 2 pieces. That seems like a hard problem because it starts with any curve, and there's lots and lots and lots of curves that you could try and write down. But here's a cool idea. Cool idea is maybe it's not going to make sense right away, but I promise it will. Take your donut, find one loop that's stuck, and we're going to unroll our space along that loop. We're going to cut it, and we're going to like unroll. So here, I can cut the torus and unroll it into a cylinder. The torus, there's 2 stuck loops that I can see in my picture here, the yellow loop and the green loop that are stuck on the torus. Of course, there's probably much more, but I know about these 2. I cut along one of them, the yellow loop. Unrolled it. Now there's only one loop that's stuck. I have a cylinder. Now what am I going to do? I'm going to cut along the green loop and unroll that into the plane. Now those 2 stuck loops are gone, and my space changed. It changed from the donut into the plane. Seems like a weird game to play, but said, promise, there's something cool going on here. What's going on is this plane keeps track of all the loops. If I have a loop on my donut that doesn't go all the way around the green loop or the yellow loop, I can draw it in one square in the plane. But what happens to the green loop? After I've unrolled the green loop, it goes from one square to the next square because I had to unroll it as I cut the surface. If I go around the green loop twice, when I unroll that, it goes 2 times in the green loop direction. The yellow loop also got unrolled. When I unroll the yellow loop, it goes in the vertical direction. What about this loop? I didn't even cut along this loop. This is some crazy, weird, spirally loop on my surface. But what does it do? It goes 1 time around the green loop and 1 time around the yellow loop. And so unrolled, it goes one time in the green direction and one time in the yellow direction. Actually, every single square in this picture captures some number of times around the green direction and some number of times around the yellow direction. And so the way we can find all the loops on the torus is to unroll the torus and realize the collection of all the possible loops looks like the Euclidean plane. It looks like a grid. And then we can ignore the loops themselves. And what we do in topology is we say we can study this grid. This grid has all the information of my surface. I wasn't originally thinking about geometry, but the Euclidean plane showed up when I tried to think about loops when the torus unrolled into a square. And for people in the know, we call this the fundamental group in topology. This is a way of calculating the fundamental group of your space. You unroll it, and you look at the pattern that unrolled. And that's all great. It worked for the donut, but how do I unroll something like this? Well, I can try my same trick. I can find some loops on the surface that are stuck, and I can try and cut along it, right? That's what worked for the donut. I found two loops that were stuck, and I cut, and then the donut fell apart into a square, tiled the plane, held all the secrets of the donut. Here, how many loops are there? I have two donut holes. Each donut hole has two loops. There's 4 loops. What happens when I cut on all these loops? How many sides am I going to get? On the torus, I cut along 2 loops, and each loop gave me 2 sides. I got a square. Here I have 4 loops, so I cut along it, and I get an octagon. My shape falls apart into an octagon, which is great. This says, oh my gosh, all I have to do is unroll with octagons. Unroll with octagons in this direction. That's going to capture all the loops that went that way. But I also need to unroll with octagons in this direction, right? I need to unroll with octagons in every direction because I'm trying to unroll my whole shape. This seems bad. How many octagons need to fit around each vertex? On the square, on the torus, we had 2 curves meeting at a point. So 4 squares met there. Here we have 4 curves meeting at a point. So we can look at that point and count how many regions there are. 8 octagons need to fit around each vertex. If a single vertex has 2 pi worth of angle, what do we need? We need 2 pi over 8 to be the angle of our octagon. We would need our octagon to have angle 45 degrees, which is not the greatest because octagons don't have angle 45 degrees, right? Like Euclidean geometry, sad. In fact, in Euclidean space, you can't even fit 3 octagons around a point. And I want to fit 8. So old me would have said, old me being mathematicians of the old geometry before 200 years ago, would have said, impossible. Can't do it. I can't even fit 3 octagons. Definitely can't fit 8. This approach won't succeed. New mathematicians, post the 1800s, now that we take curvature seriously, say, what have I learned? I've learned that in flat space, there's not enough room to put 8 octagons around every point. What should I do? Should I make space positive or negatively curved if I want to fit more octagons? Negatively curved. I should make it negatively curved. There's more room in negative curvature. So great, let's do that. Let's pick the negative one. You can do some math and you can figure out, sure, there are octagons that fit. There's enough room to put the octagons when you put negative curvature. And here's what you get. You get a tiling of the hyperbolic plane by octagons. I know this looks weird. All these octagons are actually the same size. This is kind of like the Mercator projection, but for hyperbolic space. You know how Greenland is actually 14 times smaller than Africa, but they look the same size on our childhood maps? All these octagons are the same size, even though the ones on the outside look tiny. So we took the torus and we unrolled it into the plane. We can study a torus instead by studying the geometry of flat space. We took the double donut And we unrolled that into octagons. Octagons, we needed to fit lots of them, so we needed negative curvature. Actually, for every other surface, we can do the same thing. A theorem from the early 1900s called the uniformization theorem says this always works. You can study all surfaces surprised by using geometry. The sphere is the sphere that has positive curvature. The torus unrolls into the plane. And everybody else who's really complicated, unrolls into negative curvature because it needs a lot of space. So what happens in 3D? In 3D, we could build weird, twisted, three-dimensional spaces, just like you could build weird surfaces. One of those spaces is the 3 torus. Instead of a square, this space unrolls into a cube. And you can unroll that into a tiling of space. We can study a space called the 3-dimensional torus using geometry. It unrolls into flat space full of cubes. We can also find weird 3-dimensional spaces that unroll into something like a dodecahedron, where you need to put lots of dodecahedra around. Now, you can't tile space with dodecahedra. They're too big. They don't fit. So you need to make space negatively curved. And if you make space negatively curved, then you can fill it with dodecahedra. But this isn't all. In 3D, weird things happen. In 3-dimensional space, you could also build a space that's a stack of surfaces. What geometry would this have? If I have a stack of surfaces, each surface unrolls into the plane, right? Each surface unrolls into the hyperbolic plane. A stack of surfaces unrolls into a stack of hyperbolic planes. We need other spaces. A stack of tori with a twist unrolls into a twisted stack of planes. That crazy space with the bullseye-shaped Earth we saw earlier. Here's an unrolled, twisted donut. And all of this math led to an amazing conjecture by Thurston in the 80s saying that all 3-dimensional spaces could be understood this way, could be understood using geometry. That conjecture had a $1 million bounty on it. One corollary of that conjecture was worth $1 million. It was a problem that had been open for about a century, and it was solved using geometry by Perlman. So this is an example to me of something that, like, starting out doesn't sound like it has anything to do with geometry. But we secretly found geometry inside of the problem by unrolling spaces. And that's the sort of math that really excites me. So at the end, I want to show you one more quick application of this. That application has been going on for a while. I want to show something I'm personally very excited about and invested in these days, finding geometry in high-dimensional machine learning contexts. So here's what I mean. Instead of starting by thinking about geometry, if I'm thinking about data, if I'm thinking about relationships between data, usually where I'm starting is by thinking about a graph, where the vertices are maybe data points that I have of some sort or some sort of information, and edges are relationships between them. So these are the fundamental objects I'd be thinking about if I was encoding data in a graph. One thing you want to know is maybe how similar two things are. I want to know these 2 points in the graph. I want to know how similar they are, how close they are together in the graph. And the way we measure that is by something called the graph distance. Here's how I measure distance in a graph. I find all the different paths I could draw in the graph. So here's a path of length 4. Maybe the distance is 4. I can definitely get from green point to green point with 4 units of distance. But I can also do it with 3. The graph distance is going to be the shortest possible path that you could go on. Here in this graph, the shortest path between the green vertices is length 2. So the graph distance is 2. And so the math question here is, that's hard to compute, right? Like if you have a graph, like imagine this thing had 10,000 vertices in it. And I give you 2 of these vertices and I ask you, how far apart are they? How many paths are there between them? Which one's the shortest path? Or other quantities you might want to learn about a graph. Things can be hard to compute. But we can bring geometry into the problem. We're measuring a distance. Let's try and make this distance easier to measure. I could take a graph like this, and sometimes I could find a nice way to put the graph in the plane. Here I've embedded my graph nicely into the plane. All the edges of my graph line up with the plane very nicely. Now what could I do if I want to measure the distance between 2 points on this? Well, this is the real distance. But that zigzag curve is actually pretty close in length to this pink curve, right? So if I want to know approximately the distance, instead of finding the distance of all curves in this big complicated graph, I could do one Pythagorean theorem between the endpoints if the graph was in the plane. Problem, not all graphs fit in the plane. This graph here, if I take a graph that looks like this and I try and put it in the plane, and I try and measure the distance between these 2 points, the real distance in the graph is they're far apart. But what does the plane say? The plane says they're close together. That's not good. There's some mismatch between my data, my graph, and the geometry it's sitting in. There's too many vertices on my graph to fit in the plane. What do I need? I need more room. I need room for my graph to spread out and feel comfortable. I need negative curvature. In a negatively curved space, my graph fits perfectly fine. And I can actually measure the distance on the graph by measuring the distance in my curved space. So this is good news. That graph, what did I do? I put it in the plane and I measured the distance. Everything works great. This graph didn't work in the plane. Sad. But we know why. Too many points. Needs more space. What do? Give it more space. Now it works. But this has trouble too, because my original graph doesn't want that much space. My original graph was happy at home in the plane. My new graph loved having lots of space to spread out. But my old graph can't live there. There's not a one-size-fits-all solution to this problem. If I want to use geometry to speed up my understanding of graphs, I have to, for each graph, I need to look at that graph and say, where do you like to live? And then I need to put you there. That's hard because I have to look at the graph and figure out where it lives. That's what I'm trying to avoid. But what have we learned? We've learned that some graphs like zero curvature and some graphs like negative curvature. And we know from geometry, there's plenty of spaces with both. So just to see that this is a real world problem, not just a mathematical problem, here's a real data set where the vertices are legal cases in England and Wales, and the edges between them are citations, like when one case cites another case. There's some important cases that are cited by everything, and then there's tree-like pieces of less important cases. And here's a little piece of that graph. This little piece of the graph has some trouble. It doesn't want to live in Euclidean space because part of it looks like a little tree. Part of it's spreading out a lot. The part that looks like a grid is totally happy in Euclidean space, in flat space, but not the tree. But it also doesn't want to live in hyperbolic space. Because now the tree fits nice, but the grid does not. So this tells us we can't even just look at every graph and ask you where you want to live. Some graphs don't want to live in any of those options. But studying geometry over the last 2 centuries has taught us about all these spaces that have different curvature in different directions. So now we know where graphs like this should live. They should live somewhere like this. They should live somewhere that has some negative curvature for the tree-like part to spread out, and has some flat spaces for the grid-like pieces to feel at home. And there's spaces like these. There's higher dimensional analogs of a stack of hyperbolic planes where you can actually make this work. So this is a project I've been involved with for the last couple of years with a big group at Heidelberg and now Max Planck Leipzig. So if you want to read more about this stuff, check out some of our papers there as well, or ask me questions after the talk. Anyway, that's the story. That's both the geometry I love and 2 big use cases we found for it. Thanks so much for coming on the evening.
All right. Thanks very much, Steve, for a fantastic talk. We do have time for a couple questions.
Can you have a guess an idea of the dimension of the space where it fits on the graph?
Oh, that's a good question.
Question was, can you guess the dimension of the space where the graph would fit?
Yeah, like depending on the size of the graph, how big of a dimension space you need. For the examples we've been doing, we've actually just been like relatively low dimensions because we've been working with fixed data size. So I don't have any asymptotic like. Well, in hyperbolic space you need 2, right? Yep. Yeah, most of our guys are putting in like 30. They might have lots of different flat and tree-like pieces that like need different symmetric spaces, particularly symmetric spaces for the symplectic group. Okay, well, let me see if other people who aren't coming to dinner have questions too. Does anyone have questions?
All right. If you have any questions, Steve will be here.
Yeah. Feel free to just come up.
So come down. All right. Let's have another round of applause for a fantastic talk.